In this video, we're going to talk about mathematical induction. So mathematical induction is another way to do a proof. We're going to do this kind of by example and introduce the process while we're going. So the example I've chosen is this formula. So we're taking the sum from 1 to n of n integers. So basically we're summing the first n integers, and this formula claims that that sum equals n times n plus 1 divided by 2. Okay, so to do this proof, first thing I need to do is introduce something which we're going to call p of n. So I'm going to let p of n equal the sum of all positive integers up to n. Now, forgive me, I'm using a different writing instrument, so I might be writing a little bit slower than normal. I apologize. So what this formula then means is if I were to quote unquote plug in 3, right, p of 3, that means I'm summing the first 3 positive integers, which means I'm summing 1, 2, and 3, which if I add those together, that comes out to 6. And then I'm going to look at p of 4 just to kind of reinforce this. So this time I'm summing 1, 2, oops, just kidding, 1, 2, 3, and 4, and that sums to 10. Okay, now what I'm interested in is, do these, the values I just got, could I have gotten them if I plugged it in the formula here? So in this case, n is 3. So because I'm summing the first 3. So if I plug that into the formula, I get 3 times 3 plus 1 all over 2. So that's 3 times 4, which is 12, and 12 divided by 2 is 6. It worked. Okay, here n is 4. We're summing the first 4 integers. So 4 times 4 plus 1, which is 5. That comes out to 20. Divided by 2 is 10. So it works. All right. So far, this formula does seem to work for the first 4 integers at this point. Well, I've done 3 and 4. I haven't looked at 1 or 2, but the idea is, does it keep working? Does this formula keep holding? And here's where we're going to use mathematical induction. So we have 2 steps with mathematical induction. We have what's called the basis step, and that is that we show p of 1 is true. So we're going to look at the very first case when n equals 1. Then we have what's called the inductive step. In this step, we are assuming it's true for p of k. And then we will show it's true for p of k plus 1. So let me just kind of take a second and explain why this proves it. So when you show that the first case is true, it's like, okay, case 1 is done. Then you're making this assumption. The assumption is that you're going to assume it's true for all p of k, up to the kth integer, whatever that is. And then we're going to show it's true for the next integer down. In other words, we're going to prove that if you assume it's true for the first k integers and you go 1 more integer, the formula works. And the reason this is successful is because we're building on p of 1. Because we showed p of 1 is true, p of 1 is like assuming k equals 1. So then when we show k plus 1, then we're showing that it's true for p of 2. So by showing that it works for p of 1 and assuming it works for that case, or any case that we call k, and then showing it works for the next case, then we have basically built up the foundation. So again, if we show that it's true for k equals 2, then showing it's for p of 3, we're showing it for the next step. So that's kind of the idea here that we're building. We're building the book likes to refer to it as a ladder, but we're using this kind of ladder to show that the formula holds. Okay, let's actually do it. Let's do the induction step. Actually, we're going to do the whole proof. We're going to start from scratch. So proof, and when I do this, I always like to say by induction. I'm proving it by induction, just so anybody reading this knows what tactic I'm using here. Okay, so first step then is to show that P of 1 is going to work. So in my formula, P of 1 means I'm looking at just the first integer, which equals 1. Okay, great. Now I'm going to go ahead and plug 1 in for n in the formula. Just scroll back up here. So we're doing 1 times 1 plus 1 all over 2, which comes out to 1 times 2, which is 2, divided by 2 is 1. Cool. It worked. Nice. So we have shown that P of 1 is true. Now I'm going to assume that it works up to the kth integer. So here, sorry, I'm going to give myself one more space. P of k equals k times k plus 1 over 2. I'm assuming this is true. All right. Now I'm going to show it works for P of k plus 1, the next term. Okay, so let's look at P of k plus 1. So that means we are adding the first k plus 1 integers. So here's k, and then we're going one more beyond k. So we just assumed already that these first k integers use this formula. So I'm going to plug that in for the first k integers. According to my assumption, these should add up to k times k plus 1 divided by 2. So I still have, though, this extra integer, and I'm going to go ahead and add this in. I'm going to go ahead and do a little algebra here. So I'm going to get it to be LCD of 2, combine some like terms in the numerator. I might go ahead and work a little to the side since I don't have that much space. So this is going to be k plus 1 here. I'm going to leave this alone and just simplify what's going on over here. So this is plus 2 times k plus 1 all over 2. So I just kind of thought of this as over 1 and just wrote it as a distribution. Now, the reason I did that is I'm going to factor out the k plus 1 here. Those two terms have a k plus 1 in common, and I'm left with k plus 2 all over 2. But this right here, what I just found here, this is what would happen if I plugged k plus 1 into the formula up here. If I plugged k plus 1 into here, this would have been k plus 1 times k plus 1 plus 1, or k plus 2. So if I had plugged k plus 1 into this formula, this is what I get out. And that is what I'm left with. So this worked for the formula. It showed that I end up with the formula I'm supposed to end up with for k plus 1. I'm done. I did it. So by assuming that P of k works, I was able to show that the next term is going to work. Which means because I have this basis step for showing that the very first term works, I have created this kind of building block where if the first term works, then the second term is going to work, because I just showed that I'll always get out the second term working, the next one beyond working, because it ends up building on itself. So this is the kind of ladder that the book was talking about. So this is the first step. And then we were able then to assume, based on what we just did, that the second one is going to hold, which means that because we're always building on this k plus 1 being the next term, each next step is going to keep working forever. All right. I wrote down the summation of the formula kind of nice and neatly here for you. This is using the terminology we've had with the implication on the inductive step, okay? And there is a way of expressing this as a rule of inference. Let me go ahead and write that down. So what we do is we show P of 1, and we show that for all K, P of K implies P of K plus 1. That if we assume P of K works, the next term is going to work. And all of this then shows that regardless, it works for every value, period. It just works in general, because we're kind of building this ladder from the first step on. Okay, let's look at an example. It's kind of a little bit different. Conjecture and prove a correct formula for the sum of the first n positive odd integers, and then prove your conjecture. So we're adding n odd integers, so the odd ones. All right, so I'm going to kind of start the same place. I'm going to create a P of n, and this time P of n is the sum of the first n positive odd integers. All right, there we go, P of n. Okay, now real quick, before we kind of get going into this, I want to recall some information about odd numbers that we've talked about previously. An odd number can be written as either 2n minus 1 or potentially 2n plus 1. 2n plus 1 being that it's like the next odd number. Because if I plug in anything for n, like if I plug in n equals 1, I end up with getting 1. If I plug in n equals 2, I end up with getting 3. If I plug in n equals 3, I end up getting 5. So it's listing out it's listing out the odd integers, 1, 3, 5, 7, where this is the first one, second one, third one, right? Meaning n equals 1, n equals 2, n equals 3. All right, just wanting to kind of review that concept before we get going here, because we might see that pop up if we're trying to create a formula. All right, before I do that, I need to kind of play with this P of 1 business here. So P of 1 means I'm looking at the first odd integer, and that's 1, done. P of 2, excuse me, that means I'm looking at the first 2 odd integers, and that comes out to 4. P of 3, I'm looking at the first 3, so I'm adding a 5, and that then comes out to 9. Now, right now, I'm looking at these answers, and I'm trying to think of a formula to create them, or at least notice a pattern between them. Okay, P of 4 is going to end up being adding the first 4 odd integers, and so that's 1, 3, 5, 7. So that adds up to 12 plus 4, 16. And then P of 5 is 3, 5, 7, and 9. So I'm adding 9 to 16. That ends up being 25. Okay, so I'm going to pause here because I do see a pattern. All of these numbers are perfect squares. That's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. It's literally going in order. And look, hey, that connects to the 1, 2, 3, 4, and 5 over here. So I think that the odd numbers are adding up to, sorry, let me write it down. 1, 3, 5, ... up to 2n minus 1, whatever that is, that these add up to n squared. Okay, or P of n is n squared. Okay, let's prove it now. Oops, let's prove that it works. Sorry. Okay, let me erase. There we go. Proof. Again, I'm going to just say that I'm doing induction. So anyone seeing this will know what I'm doing. Steps I'm taking. Okay, step one. We're going to show it's true for P of 1. So P of 1 is the first odd integer, which is 1. And when I do 1 squared, it comes out to 1. So boom, it works. First step done. Now I'm going to assume it's true for P of K. So I'm going to assume that P of K equals 1 plus 3 plus 5 plus ... plus 2k minus 1, that equals k squared. I'm stating here in my proof the formula I'm basically using. All right, cool. Now I'm going to show it's true for P of k plus 1, which means I'm going one more odd number out. So one more odd number out is the k plus 1 odd number. So I'm doing k plus 1 in here. Now, just so we can simplify this right here, this actually simplifies to 2k plus 2 plus or minus 1 ends up being 2k plus 1. If I just simplify that this thing right here, that simplifies to 2k plus 1, which look, totally makes sense if the previous odd integer is, 2k minus 1, right? It totally makes sense. Okay, because I'm adding 2 every time because I'm skipping 1. 5, 3, and 1. Okay, written it all backwards now. Okay, but we happen to know from our assumption that we are saying that this right here does in fact equal k squared. So this all is k squared. But I'm still adding 2k plus 1 to it. Okay, actually, that's a quadratic and it factors. So I'm doing a little algebra here. It factors into k plus 1 times k plus 1, which happens to be k plus 1 squared, which is what I wanted. I wanted to show that when I add up to the k plus 1, it ends up getting k plus 1 squared. Yay, we did it. So we did find the formula. It worked. Okay, let's try another example. So this time we're told to prove that n is less than 2 to the n for all positive integers, that inequality will always hold. Okay, by induction. Oh, wait, actually here, before I do that, I'm going to state P of n. Oops, what got mad at me for writing that? I'm sorry. State P of n. So here, just I'll put it into the proof itself. So let's let P of n equal, oh no, not equal. Let P of n be the proposition, because we're going to kind of state it differently. I'm sorry, every time I erase, it gets mad at me. Let P of n be the proposition so we'll do it in proposition form, that n is less than 2 to the n. Okay, so let's proof by induction. I'll write that down. Using induction, P of 1 is going to be, true. Ugh, I'm scared to actually write that. Sorry, let me go ahead and try doing the backwards. There we go. Okay, P of 1 is true because 1 is less than 2 to the 1, which is 2. So that's true. Boom. Okay. So now I'm going to assume P of k is true, which means I am assuming that k is less than 2 to the k. Cool. All right. So now I'm going to show that it works for k plus 1. Okay, to do that, I'm going to start with my assumption. I need to kind of start here because I need to build an inequality. If I add 1 to both sides, the inequality holds because I've increased both sides by 1 at the same time. What I'd like to do is manipulate the right side here, this side, so that this ends up being less than 2 to the k plus 1. That's what I want to have happen, okay? Like at some point, I want 2 to the k plus 1 to pop out. All right, so to do that, I need to manipulate this inequality. I can say that 2 to the k and 2 to the k works. In other words, I know that 1 is definitely less than 2 to the k, because the first case worked when k happened to be 1. And since k is a positive integer, I'm good. Like it's always going to be less than that value, regardless of which k I'm looking at. So I can say that this statement right here, 2k plus 1, is definitely less than 2 to the k plus 2 to the k. All right. But this is 2 to the k's, right? I have 2 of them. So that's how I write it. I have 2 times 2 to the k. But that 2 here is technically an exponent of 1. And when I have matching bases, I can add the exponents. So this ends up being 1 plus k, or k plus 1. And I did it. I showed that k plus 1 is less than 2 to the k plus 1. Therefore, I shouldn't write so again. That just seems redundant. Therefore, P of k plus 1 is true. And we're done. We did it. We showed that the k plus 1 case works. All right, let's try another one. Let's do 2 to the n is less than n factorial whenever we're looking at numbers bigger than or equal to 4. So 4 is the starting point on this one. So on all of the last ones, our starting point was 1. But on this one, our starting point is 4. So when we do our basis step, we're going to look at 4. Okay, so I'm going to create a P of n again. So let's let P of n be the proposition that 2 to the n is less than n factorial. And I should say for n bigger than or equal to 4. Probably should make that statement. Okay, cool. Now let's use induction. Let's do this. So first thing, I'm going to show that P of 4 is true. So not P of 1, P of 4, because our starting point is different. So P of 4 is true since 2 to the 4 is less than 4 factorial. Because remember, 2 to the 4 is 16, and 4 factorial is 1 times 2 times 3 times 4, which comes out to 24. And 16 is definitely less than 24. Woohoo! Done. Now we're going to assume P of k is true. In other words, 2 to the k is less than k factorial. Okay. Now that we kind of have seen what it looks like based on the last example, how you kind of build up an inequality, I'm going to start with what I'm after, and I'm going to manipulate it to get what I'm interested in having be true. So I'm going to start with 2 to the k plus 1. 2 to the k plus 1. I want to show that this is less than k plus 1 factorial. Okay, so to do this, first I'm going to write this is the same thing as 2 times 2 to the k. I'm literally using what we just did in the last proof, right? I just pulled off the 1 and wrote it as a 2. Okay, but 2 to the k, we've assumed is less than k factorial. So this is less than 2 times k factorial. I'm going to drop the parentheses. Times k factorial. Cool. Okay. So that's based on our assumption. Okay. Now I'm going to cheat because my goal is to make this a k plus 1 factorial. And just so we're clear, the k plus 1 factorial is the k factorial. Oops, not plus. Not the k factorial. All the way up to k, but one additional k plus 1. So it's timesing the k factorial by k plus 1. Okay. I just wanted us to see that. Okay. So I'd like to turn 2 into k plus 1. So my question then is it reasonable to say that k plus 1 is bigger than 2? And the answer is yes, because k starts at 4. So the smallest number k is going to be is 4. And that's clearly, sorry, that's supposed to be a less than or equal to. There we go. That's clearly, no, bigger than or equal to. Oh, it's going to get mad at me because I'm using the eraser. Oh, it didn't jump. Yay. So bigger than or equal to 4. So minimally, this is going to be a 4, which means 4 plus 1 is 5. And 2 is clearly less than that. So regardless, in the minimum amount that k is going to be, it works. The inequality holds. 2 is going to be less than k plus 1. Therefore, this is k plus 1 factorial. And we did it. So P of k plus 1 is true. And we completed it. All right. One more example. Use induction to prove that n cubed minus n is divisible by 3 for every positive integer n. All right. So similar start off. There's a proposition going on here. Let P of n be the proposition that they just gave us. That n cubed minus n is divisible by 3. Ooh. Divisible by 3. And that's for every positive integer. I'm not going to state that just because I don't want to write it down. Okay, cool. Got lazy on you. Let's using induction. P of 1 is true. So let's show it's true because 1 cubed minus 1, when I plug in the formula, comes out to 0. And 0 is divisible by 3. All right. Step 2. Assume P of k is true. Which means I'm assuming that k cubed minus k is divisible by 3. Awesome. All right. Now we're going to show what happens when we use k plus 1. Okay, so P of k plus 1. That means I'm looking at k plus 1 cubed minus k plus 1. So I want to show that this thing is divisible by 3. I need to do the algebra now. So this equals, okay, so this is k plus 1 times k plus 1 times k plus 1. Now, I'm going to show the work for this, but it is possible to skip some steps if you feel really comfortable. Oh, I just realized that should be in parentheses. So, because we're going to distribute a negative there. All right, let's get to multiplying. So k plus 1 times k plus 1, when you FOIL, comes out to k squared plus 2k plus 1. All right. Okay, now let's multiply those two. And you can again take my word for it. This is going to come out to k cubed plus 3k squared plus 3k plus 1. All right. And that's minus k plus 1. Okay, so here, let's go ahead and distribute that negative in and combine some terms. So this is going to be k cubed plus 3k squared plus 3k plus 1 minus k minus 1. So the ones cancel completely, and it combines with 3k to be a 2k. So, there we go. Oops, plus 3k squared plus 2k. All right, cool. That's what we got this simplified to. Okay, now my goal is to show that this thing is divisible by 3. And I'd like very much to get the assumption k cubed minus k in here, because that I know is divisible by 3. So to do that, I'm going to be tricky. I'm going to use something called a put and take. I'm going to put something in and then immediately take it away. Here's how that works. Because I liked it to be k cubed. Oops, I'm sorry. I thought I had switched back to red. Okay, cool. Switch back to red. Thank you. I'd like it to be k cubed minus k. I'd like that to be here. So I'm literally kind of shoving in minus k right there after the k cubed, which means because I'm putting in a minus k, I need to compensate by taking and adding k as well. So here's what I put in and took away at the same time. I put in a minus k and I took away a k at the same time. Now here's what that does. This is what I was after. This is my assumption. And I know that that's divisible by 3. Over here, I have 3k squared plus 3k. But look, both of those are also divisible by 3 because they have a 3. So here, a nicer way of writing it is to factor it out. Factor out the 3. And then I'm like, see, this thing is divisible by 3 because there's a factor of 3. All right, so here we go. I'm going to write that down, what I just said. So this is divisible by 3 because of the assumption. This is clearly divisible by 3 because it has a factor of 3. So I'm not going to write that because it's divisible by 3 since it's got a factor of 3. So we can now assume that k cubed plus 1, I'm sorry, I wrote that wrong, not k cubed plus 1. Oh, it got mad at me. I'm so sorry. It's just upset because I'm clearing it. I'm so sorry. Okay, we can now say that k plus 1 cubed, there we go, minus k plus 1, what we started with, is divisible by 3. So P of k plus 1 is true. And we're done. We were able to show it was true using induction.